camera on there? Camera on? Yeah. Camera and microphone are on. Okay. Yeah. Great. Excellent. Okay. Well, welcome back. Took a lap. Right. Well, it's nice that many of you could join us. So we'll be continuing our discussion of ray tracing today. Let's see here. In terms of your course announcements, your quiz continues to approach, right? It's right before the drop deadline for this course, which is on purpose. So you can take your quiz. We'll try to grade it quickly, and you'll get a response in case that's a useful data point. And again, as yet another reminder, your project proposal we do the same week. So consider yourselves warned. Let's see, your simulation assignment was due yesterday, I believe. So your next one on ray tracing should be out, and that's a fun assignment. Like I would say, if you guys, for those of you who like to do extra credit, which is usually decorrelated with the people that need extra credit, this is a good assignment for that. There are lots of cool extensions for ray tracing that you can think of. Any questions before we get started with graphics for the day? Cool. Okay, so the last couple lectures we've been talking about rendering. Hopefully we remember that much. And in particular, we've covered one algorithm for rendering. Remember that the rendering universe roughly divides into two pieces. There's ray tracing and there's rasterization, right? And so far, we've been talking mostly about ray tracing, where you kind of draw the world one ray at a time. And then later we'll talk about rasterization, where you draw the object, the world kind of one object at a time. Right? So in ray tracing, we've come up with these algorithms which can really capture some pretty impressive effects, right? With not that much code. Like what you'll see in your assignment is that you get some really nice looking images, and it's really, I would argue, not so difficult relative to the complexity of the images that are coming out of your ray tracer. But of course, as you do that, you pay in computational efficiency, right? And so what today our lecture is all about are different data structures and approaches to making your ray tracer fast, which of course in practice is extremely necessary, right? You won't be able to do much without it. So there's a little bit of a recap. Here's our basic ray tracing algorithm is that you have one function to rule them all, which is this trace ray thing, which is given an origin and a direction. It just tells you the first thing that your ray bumps into and what the color is. And like we've covered in the last couple lectures, of course, this is a recursive kind of scenario, right? So for instance, if you want to have shadows cast on your scene, you maybe cast a secondary ray toward the light and see if it runs into something in between you and the light source, right? Or if you want to do soft shadows, maybe you send more than one and so on. Right? So that's our algorithm so far. Probably the most concrete example where you really have recursion in your code is reflection, right? Because of course, when the ray bounces into the reflective surface here, in order to figure out the color of the surface here, what do? You reflect the ray, and then you just kind of keep moving. Right? And indeed, in your assignment, you'll implement this, and depending on your number of bounces, you'll see more and more stuff in your scene. And that led us to this object, which isn't really a data structure as much as just kind of a visualization, which is something that we call the ray tree, which is basically just this idea that with every ray that you send out, it spawns a bunch of new rays. And so this forms this kind of tree structure, which is describing all the computations you do just to render a single pixel, right? And as we know with trees, they tend to grow exponentially, as you move toward the leaves. And that's really what's causing the big computational challenges that we have in ray tracing. Okay, so what did we do in case this wasn't complicated enough? Well, at the end of our last lecture, we came up with a bunch of cool visual effects, and we talked about how we could cope with those in ray tracing, right? So, for instance, if we want anti-aliasing, soft shadows, and so on, what was basically the solution to each of these problems? More rays, right? But of course, with each ray, you pay $1 in computation time, and your rendered image gets very expensive very fast, right? So, an example of this more rays idea is maybe your light source takes up a finite amount of space, it's not just a point. So what could you do for your shadow ray? You could send a bunch of shadow rays to randomly generated points on your light source and then average the result for your lighting. Similarly with motion blur and so on. But here's our big problem. There's too many rays. In fact, if you were, you went and took, 6006, the algorithms course, which apparently I'm teaching in the spring, and you did your sort of big O style analysis, you would get a pretty ridiculous computation cost, right? I mean, essentially it's the product of all the possible things that can happen in your scene is the number of computations it would take to do the ray tracing algorithm, right? Like the number of pixels times the number of primitives times the cost of doing an intersection times the number of times you recurse times the number of shadow rays and so on, right? Because all of these things multiply together when you want to count the number of computations you have to do. So hopefully you guys can all appreciate, essentially the message you should get so far is that ray tracing is hella expensive, is the technical term here, and essentially our task today is to try and fix it. Okay, and essentially the bottleneck, at least one of many bottlenecks, but probably the main bottleneck here, is this for loop that we've highlighted in a very subtle shade of red on the screen, which is that you have to loop over every object in your scene and intersect it with your array. Right? And if I send a ray off to my left over here, I'm pretty confident it's not going to run into Colton, but so far my algorithm doesn't know that, right? The only thing it would know how to do is just iterate over every single object, every chair and student in this classroom, hit them with that ray, and then choose the closest one. One thing to note from the get-go, one kind of funny thing is, so far, our difference between ray tracing, or at least ray casting, and rasterization is basically just the order of these two for loops. But starting with today, what we're going to do is accelerate this inner for loop, and then ray tracing and rasterization are just going to become different, right? Like I'm not going to be able to use the same kind of data structures when my outer loop is over every object instead of over every pixel. So it's something to kind of keep in the back of your head and mull over a bit. Pardon me. Oh, by the way, one small announcement. On Tuesday, we will have a actually quite tall substitute lecturer by the name of David. He's one of my graduate students. The class will not be filmed. I'll be present but unable to speak. And then starting the lecture after that, your instructor, God willing, will not be so squeaky. Okay, right. So our goal is to reduce the number of ray primitive intersections. So how can we do that? Actually, before we get started, what ideas do you guys have? How can I reduce the number of ray primitive intersections? Critically a bit. Yeah.
I mean, you can cluster a bunch of primitives into a box.
Yeah. Yeah, so I could put a big box around a bunch of primitives. If my array doesn't hit that box, do I have to intersect anything inside of that box? No. There are other ideas? There are actually many things you could do, right? I mean, for instance, one thing you could do is try and do some kind of reduced precision arithmetic, reduce the quality of your math, and maybe that's good enough. Or maybe you do stuff in parallel. I guess that's not strictly reducing the number of ray primitive intersections, but those are ways to make things faster, and there are many. But actually, the strategy that we just suggested is by far the most common approach to making ray tracing faster, which is to use what we call bounding volumes, which is exactly what it sounds like. Right? So I put a big box around my bunny here, and I intersect my array with the box. If my array does not intersect the box, and I know ahead of time the box is around the bunny, probably with a little bit of padding on the outside just for fudge, then I don't have to look inside of the box, and I've just saved myself about 1,300 ray triangle intersections. Does that make sense? Notice that I also did have to pay a little bit. Right? I had to pay because I had to intersect the array with the box. So for instance, putting every single triangle in the scene in its own bounding box make any sense? No, right? So there's a little bit of a trade-off there, and you have to be a bit careful when you design these data structures to make sure that you're not just incurring a bunch of expense and then intersecting everything with your triangles anyway, right? Like that wouldn't be so great. And that's actually somehow obvious to say, but we'll see that these algorithms, they can play out in subtle ways. Yeah, Rachel. Oh, you're absolutely right. And that's a really critical question. So here's the thing. Let's say that my bunny actually occupies about 3 pixels of a, 800 by 600 photograph, right? And in fact, the bounding box, maybe it intersects 5 pixels, but that's a heck of a lot less than 800 times 600, right? So for all the remaining pixels, I only do that one ray box intersection and I'm done, right? But you're right. Suddenly, I've created a lot of inequality. Some pixels are going to take me a lot of time to render because they hit that bounding box. And now I have to look inside of it and intersect against everything inside of it. And some just are going to be very fast because the array just zipped right past the whole thing. I did my conservative computation and said, don't worry about the subject. Does that make sense? Cool. Okay. By the way, one thing we talked about earlier, I see that. One thing we talked about earlier was parallel processing, right? You can parallelize your ray tracer. What does this imply about parallel processing? Like if I launched one thread per pixel, well, it means that some threads will take a heck of a lot longer to finish than others, right? And that's absolutely true in ray tracing. And that's, in some sense, really the big challenge. Like some students in this class have already asked about GPU accelerated ray tracing. But your graphics card is this object that's like got this one hammer and just wants to hit every nail the same way. But that's somehow not the way that things work in ray tracing. The computation is extremely non-uniform over the space of the image. Yes? It's a fabulous question. So maybe I'll boil down your question a little bit to like, I haven't told you how to actually compute these boxes yet. And I promise you we're going to. That'll be most of our lecture today. Yeah. Right. So let's start with the easy stuff and then we'll dive into some details and heuristics for actually constructing these in a way that reduces the amount of computation. One thing to note that I do think is worth mentioning, let's say that I have a really, really complicated algorithm that takes my triangle mesh and comes up with like a beautiful set of bounding boxes that's somehow optimized for my camera position and everything else. But my algorithm for placing those bounding boxes takes like 2 hours to complete. Well, if I have a gajillion pixels in my scene, that might be okay. If I have a very small, low resolution image, it might not, right? So one thing to notice is that now, in addition to this very non-uniform distribution of computation, you also have sort of 2 steps in your pipeline, right? The first one is analyzing the scene and constructing these boxes. And then the next one is rendering. And if I put too much time in the first step, well, then it doesn't matter how fast the second step is. It might be that I actually already lost, right? So in some sense, you have to take the computation time to set up your scene, divide it by the number of pixels, and add that to the per pixel time to get an accurate sort of understanding of the full pipeline. And indeed, that actually is a really important point. We'll see that some of the algorithms that we talk about for constructing these bounding volumes are a little complicated. And if you implement them the wrong way, or if you have a low resolution scene, they really may not be worth it, because that setup time ends up becoming significant. Okay. Right, so the main question is, how do we actually construct these darn things? So here's a really profound thought to get us started here, which is that your bounding volume must indeed be a bounding volume. And indeed, where this algorithm could fail is if like the ears of the bunny poked outside of the box, right? Then, of course, testing against intersection with the box didn't actually do anything, right? Like I could miss stuff inside. But if we step back, one thing to notice, you know, is your bounding volume does not have to be a box. It can be just basically anything that's easy to intersect with array, right? So in this class, we've talked about planes, so it's not going to be too hard to extend that to a box. We'll talk about that in a minute. Bounding spheres are totally reasonable things. Probably depends on the isoperimetric ratio of your surface, right? You have like a kind of spherical object or like kind of a boxy one. Which of those bounding objects is better? There's some complicated algorithms that will do things like cut out a convex region, so like a bunch of half planes and so on. But again, the more complicated your model is, the more time it takes to set up and to intersect your array against the bounding volume before you've even hit the actual things you care about, right? Okay, so the most common object for bounding volume is also the least interesting, which is a axis-aligned bounding box. When I say axis-aligned, like I could take a rectangle and like rotate it 30 degrees, right? But then intersecting array with that rectangle would be kind of annoying. So instead, usually our bounding boxes are just aligned with the XYZ axes to keep our computation simple. Because remember, these are just heuristics for throwing away computation. I mean, there are notions of optimality here, but we really haven't touched them. Okay, so we should spend a few minutes talking about how to intersect array with a box. This is a really boring computation, so bear with me. I think it's one of those ones where if you start writing down the symbols, it's easy to look complicated, and then you step back and say, well, wait a second, you're just intersecting array with a box. Like, you guys can probably code this off the top of your head. But in any event, let's do that real fast. So, first, how do we specify a box? Probably from its like lower left corner to its upper right one, right? So a very typical one would be the smallest XYZ coordinates and the largest XYZ coordinates. And then your box is like the range from X1 to X2, cross product with the range from Y1 to Y2, cross product with the range from Z1 to Z2. That makes sense? Cool. And of course, we have a array, which we have all agreed is best represented using an origin point and a direction. And so our task is to figure out, does my array careen past this box, in which case I can ignore it, or do I have to look inside this thing? So of course, the naive thing to do here is that your box is just 6 planes, and we already talked about intersecting arrays with planes, so you could work out the equation of each of these objects, intersect your array with each of them, and then figure that out that way. And by the way, that's more or less what we are going to do. But we can simplify that computation quite a bit in the case where our box is axis aligned, right? Which also makes sense, right? Because like, what is the normal to each of those faces? Well, it's like plus x minus x plus y minus y plus z minus z, right? So you don't need to do all these fancy dot products we were doing in our past lecture. Okay. So let's see if we can reduce this computation quite a bit. And there are many ways to do it. So for instance, we can notice that pairs of planes have the same normal direction, and that our normal vectors only really have one non-zero. So do we really need 3 multiplies and divides? No, we just need 1. It sounds goofy, but in ray tracing, every add and multiply counts because it gets done so many times. And so actually people really do think quite carefully about every single operation. By the way, the really expensive ones tend to be square roots and trigonometric functions. In fact, do you know this really neat trick there's this sort of discovered mathematical formula inside of the code for Doom, the video game, for an approximation of square root that like involves like shifting bits around and like all kinds of crazy stuff. Yep. It has its history in graphics, and somebody just guessed this weird formula. Yes, you're okay. One thing to watch out for, geometry is full of special cases. This is no different. If you happen to be looking right down the axis, you run the risk of divided by 0 if your code isn't careful. Okay, so in any event, what can we do if we want to intersect an array with a box? Well, remember we did CSG stuff before. And how did we do CSG? Well, as we already saw in our quiz today, it's essentially just a bunch of one-dimensional computations, right? And in this case, our box is really, really simple. It's just like a range of x values, a range of y values, and a range of z values, right? So the intervals for like the 2 horizontal planes, the 2 vertical planes, the 2 z planes, I feel like I'm doing that Madonna music video, are all very easy intervals to compute, because essentially you're just trying to figure out when does my array have x coordinate this, and then at what time does my array have x coordinate that, right? And that's my range. And so that's what our computation looks like. So for instance, in the x interval, notice that the blue line extends past the outside of the box. Then I do the same thing for y, and then I put them together, and I get the purple one. But this is exactly the same strategy we talked about for CSG. Cool so far? The high-level story makes sense? Neat. Okay, so of course in 1D, we have a picture that looks something like this. So our horizontal axis here is time, right? This is like my photon running along my array. And I have the interval while I'm inside of the array in the x coordinate, the y coordinate, and the z coordinate. What should be the start time for my box of all these different little circular dots marked here?
Goes up for the blue.
Yeah. So in particular, it's sort of the max of the left points of the intervals, right? What should be the end point? The min of the right. Yeah. And of course, those could be swapped, right? Like these intervals might not overlap, in which case your intersection is empty. Yep. And then you can say, aha, my array did not hit that box. You know, I will not eat it with the fox. I don't remember the rest of that poem. And I don't have to do computation inside. Okay. Right, so essentially the only task we have left is just computing those t values for these different axes. And of course, that formula is very, very simple, right? Because your array is nothing more, it's just a linear function, right? Your x coordinate is just x naught plus t times the x coordinate of the direction, for example, right? So essentially, in fact, we can just do it, right? So remember that your array is like what? P of t equal to p naught plus t times the direction, right? So if I have like x0 is like the first x coordinate of my box, then what would be the system I solve? It's like x0 equals p0x plus t dx. I solve for t. I'm sorry, we've used r's here instead of p's, but whatever. And then what I'll get is that t value. Does that make sense? I think we've done these computations enough times. We gotta get the idea. Yep. So that gives you an interval, and then you compute the next interval, you intersect. One small hack, because again, every computation matters, is let's say I have two intervals and they already don't overlap. Do I have to compute the third? No. Right? So I can shave off just a little bit more that way. And then we're done. And of course, if t start is after t end, so for example, in this particular scenario, then we know that we're not inside of the box. The other one we have to be a little bit careful about is if the t's do not contain the t of the eyeball, like 0. If 0 is not contained inside of the interval or to the right of that interval, then I also don't have to look at the box because it's behind me. Cool. All right. So to summarize the world's simplest algorithm in a really complicated PowerPoint slide, here we have it. So essentially you just compute those different intervals, you take their intersection, and if it's an interesting one, then you have to recurse inside of the box, and otherwise you can hop over the whole darn thing. This is not the kind of thing you should write down. This is the kind of thing that you should just be able to kind of reconstruct on a piece of scrap paper. All right, any questions about ray box intersection? I know I kind of zipped through that. I think this is really one of those things that like is easy to get yourself confused staring at a slide, but like in practice, you're just intersecting lines. It's really not so bad. Excellent. Okay. One small efficiency trick here. Take a look at all these formulas. I never actually need r sub dx. What I need is 1 over r sub dx. And on many CPU architectures, division is ever so slightly more expensive than multiplication. So maybe what I do is rather than storing the direction of my array, I actually store the reciprocals of each of those coordinates and multiply each time, because any tiny bit of savings counts. On the other hand, the precision of this computation is probably a little bit worse. Okay. We good so far? All right, so that's how to intersect bounding boxes with things. Now, the next thing, to return to the question we had before, is like, well, where do we put these boxes? Like, how do we come up with a reasonable configuration so that we actually have some savings? Let's start easy. We want a bounding box of a triangle. What do? Well, triangles are nice convex shapes, so it's enough to take the bottom edge of the bounding box to be the min of all the coordinates, upper edge to be the max of all the coordinates. You can convince yourself that the entire triangle has to live inside of that box. Is this necessarily a good bounding box, BT devs? Where good means like somehow like a useful bounding box would be one that like is kind of slim on the piece of geometry that I care about. No, right? So as a good counterexample, right? If I have a giant sliver of a triangle and that triangle is not axis aligned, this is actually okay if it's like horizontal, right? Then my bounding box will be, oh boy, something like that, right? Which means that there's like all kinds of rays that intersect that box and don't intersect the triangle. So somehow it's not a very useful bounding up. Yeah?
Can we keep this then like parallel to that and not have all of that?
You can. Yeah, that's an excellent question. Can you have it all? Can you have it parallel to the axes and somehow not run into this issue? The answer is no. One thing you can do is if you notice, for example, a very typical thing in computer-aided design is to have meshes that kind of look like that. And maybe you discover that there's enough of them that it's worthwhile to group all these guys together, store a transformation matrix so that it becomes axis aligned, and then use your bounding boxes instead. Yeah. These are all heuristics, by the way. There's no right answer here. Yeah. Bounding box of a sphere is equally easy, and subtract the radius. I think we're good so far, and since those are the only two primitives we have in this class, we're kind of good. If you take your bounding box of a triangle to the limit, obviously a plane has no bounding box, unless it happens to be axis aligned. I probably wouldn't put a bounding box around a plane. I don't think that's a very worthwhile endeavor. And now we're going to introduce the really neat trick, which is putting bounding boxes around our bounding boxes, right? And of course, that's a very easy thing to do. You just take the min of all the possible coordinates and the max of all the possible coordinates, and that'll be the bounding box of these two smaller guys. Why is this the really critical application? Yeah.
Like just one gigantic bounding box around like your whole mesh and like basically start subdividing it down.
Exactly. We're going to have recursive bounding boxes inside of more bounding boxes to try and kind of keep winnowing down the number of intersections that I have to compute, right? So like maybe I want to first get rid of the entire left-hand side of my scene, and then in the next one I cut it vertically or something like that. We'll talk about a few different strategies for doing that. One last one that's worth noting is that if you have a transformation matrix hiding in there somewhere, and you want the bounding box after you apply the transformation, it's kind of annoying, an annoying computation to do. You have to be quite careful and conservative about how you do it. I wouldn't worry about this one a whole lot. Okay. So, question is, are we done? Like, is our ray tracer fast now? We just take every object in our scene, put it in its own bounding volume, and like, now our rendering is fast? Yeah. Yeah, for one thing, we gotta account for the time it takes to actually find the bounding object. That's absolutely right. The other one is that, like, let's say I want to like render this bunny here, and I get up in its business, so it's like taking up most of my screen here. Having one giant sphere on that bunny is really not going to save me that much computation time, right? So, like we already mentioned, what we'll likely do is build up what we'll call a bounding volume hierarchy, BVH if you're in the know, which essentially says, okay, maybe it's useful to have a bounding sphere around the bunny because he only occupies a little chunk of my screen, so I'd like to get rid of it if I can. But he still occupies enough of my pixels that it's worth taking the inside of the bunny and then dividing that into two, so that once I've determined that I'm inside of this big sphere, now I should intersect against all these little spheres and see which ones I'm in. First of all, a few qualitative things you can already notice in this picture. One is that notice that these circles overlap. So the second that I send a ray, like let's say that I send a ray into a circle and it says like, aha, you intersected a triangle. Am I done? No, I still have to look at all the other spheres, right? Because, for instance, if I sent a ray here, there are two different bounding objects that both might contain that one triangle, which is closest to my computer screen, which is the one I want to find. Yes?
In that case, would you have to like make sure you're not double drawing it, or is that like what the problem would be, or why? I'm not entirely sure I understand why we have to.
Sure. So essentially, the idea of a bounding volume is it's kind of a conservative object, right? Like, you know that if you don't hit the bounding object, then you also don't hit anything inside of it. What you're not saying is if you do hit the bounding volume, the object that you run into is necessarily the one that's closest to the screen. Yeah. The common source of bugs in code. Yeah. Okay. So anyway, this is going to inform a little bit how we have to implement this stuff in practice. We're going to be quite careful how we do it. Okay, so to return to our question from before, we got to figure out what is the best way to construct one of these hierarchies. And I imagine we could all cook up some pretty reasonable things to do, right? Like maybe we take all the triangles, we split them in half somehow, like we just take the average x coordinate, we group them that way and then do this recursively. But and for every one of these things you could think of, probably somebody out there has given it a try, and for some scene or another, that's the right thing to do. The reality is a lot of this software will actually give you the option of trying many of these different data structures because it actually depends a little bit on exactly what the objects are in your scene. Okay, so the first one we'll talk about is a bounding volume hierarchy, which is sort of the simplest one. So let's say this is called triangle soup for pretty obvious reasons. I just got a bunch of triangles floating around. They don't form a mesh, they just form a bunch of triangles. And I want to make this into a bunch of bounding volumes that are in a nice hierarchy. So one thing I could do would be put a big box around all the objects in my scene, and then find some heuristic for taking all the objects inside of this box and dividing them into two sets, right? And then for each of those sets, computing their bounding volume and recursing, right? So like this is what this might look like. Then maybe I choose that dotted line. We'll come back to how to choose that dotted line in a minute. Now I have two boxes around those two sides. Now maybe just for shake things up a little bit, I choose a horizontal line this time. So now I've got these things. Those are contained inside. And maybe I continue to split these two boxes because they have two objects in them all the way down to the bottom. In practice, do people probably go all the way to the bottom of the hierarchy? Yeah, probably not. Right? Like at some point, just looping over all the triangles in the box is a reasonable computation to do. So this leads us to a really critical question when you build these objects, which is where did I place that dotted line? Like where is the line? Is our question here. And of course there are many heuristics, right? So yeah. So does anybody actually, what are you guys' thoughts? Like how should I find a reasonable dividing line? So I have a bunch of stuff that's all in one box, and I want to take that box and split it into two boxes. Yeah. Yeah. Do they necessarily have to divide into 4 and 4? Sure. So let me give you a really evil counterexample. So here's an object. Let me make it even pointier so it's easier to draw. So here's an object. Here's another object. Here's a third object. Here's a fourth one. Can I divide it? Is there any vertical line that I could draw that divides this into 2 and 2? In fact, is there any horizontal line I can draw that divides into 2 and 2? No. Is that okay for bounding volume hierarchy? Actually, yes, right? Because it's perfectly fine to have two boxes that overlap. But if I send it right here, I'm just going to have to intersect against them both. But the heuristic that you mentioned is actually a totally reasonable one. Like maybe I take the centroid of every object and I sort them by x coordinate, then I cut it in half or something like that. Yeah. And there are many such strategies, right? So some pretty typical ones might be like, maybe just take the box, take its width, divide it by 2, and like who cares if there's more stuff on the left than the right? It's actually a reasonable strategy. Or as you suggest, maybe sort them and then cut so that there's exactly 50-50 in the two boxes. Actually a pretty common one in computer-aided design is that the person who designed the object actually probably did so with a hierarchy, and maybe you just reuse that. Right? Like remember we talked about CSG and how CSG kind of makes a tree. So maybe you just use that tree to define your bounding volume hierarchy. Yep.
What if the person is also evil? They were designing, they have like one realistic triangle over here, and then like it's ridiculous amount of space, and then like one like 8 all the way on the other side.
Mm-hmm.
Would it make sense to do something other than I don't know, somehow minimizing the amount of empty space?
That's a fabulous question. Yeah. The question, which is a really insightful one, is does it actually matter that I have 50-50 on the two sides of the box? The answer is probably no, right? Like as you say, if there's one isolated object that's far away from everything else, it probably pays to put them in their own box and then deal with the rest of my scene so I don't have like this giant empty void that's sitting there. Yeah, absolutely. We'll talk about one heuristic for that, where essentially what you'll do is you'll take your scene, and you'll take a line and you'll project all of the geometry of your scene onto this one-dimensional world, and then you'll render your scene in the one-dimensional world, and then find a cut that is trying to, as you say, to minimize the amount of space, because somehow that's what matters. Yeah, it's called a visibility heuristic. Okay, so this is how we build a bounding volume hierarchy. Notice I'm going to keep drawing these pictures in a suggestive way where the boxes intersect, because that's what's really critical here, is to remember that that can happen. Okay, but by the way, what we're going to make is the assumption that every object in my scene belongs to one box, but the boxes can overlap. We're later going to talk about an algorithm where the boxes don't overlap, but one object might appear in multiple boxes. That makes sense? There's sort of two different pictures you could have. In any event, how could I do ray bounding volume hierarchy intersection? Well, it's quite simple, right? So I first intersect with the outer box. I say, aha, my ray intersected that box. So now what do I have to do? Well, now I have to recurse and intersect with the two boxes in between. And the case that you got to worry about, by the way, drawing these slides was ridiculously annoying because it's really hard to get these kinds of things right. But here's an example where your ray is going like this. And let's say that I happen to intersect, I noticed, aha, I hit this box first. So I intersect with all the triangles in this box. What intersection point am I going to get back from that test? You guys are all pointing, and I can't really tell, but you're going to get this point, right? Because that's the yellow box. So notice that kind of an annoying thing happened, which is this is the box I hit first, but the actual first intersection belongs to the bounding box that I hit second. That make sense? So this is just a good example where you have to code these things very, very conservatively. If there's ever a chance that your array might intersect something in that box first, you've got to test on the inside of it, right? Okay, right, so in any event, there's our kind of nasty boundary case. And although it looks like I kind of constructed this, and you're absolutely right, because we're teaching this stuff, the reality is that 3D things are really complicated, and these things really do happen. Like, this is not made up. Yeah?
Why does it calculate the triangle below? Isn't it also in the first box?
That's a great question. So in a bounding volume hierarchy, we're going to make the assumption that every object belongs to one bounding box. But we're not going to assume that every bounding box, We're going to assume that every object belongs to one bounding box. We're not going to assume that the same object can be in multiple bounding boxes. So in other words, they just overlap, right? So this is kind of like having one giant rectangle in your scene with stuff inside of it, but it's saying nothing about like ordering or anything else. Yeah. Sorry, these sentences are hard to phrase and get right. Yeah. Cool. So anyway, it's just something, there's your cautionary tale of the day. Okay, so in a bounding volume hierarchy, the advantage is these are pretty easy to construct and traverse, but the disadvantage is that it can be very difficult to find that good split point, like we kind of talked about. And moreover, if we have a bad split, you might end up doing more computation traversing that tree of boxes than you would have if just intersecting with the triangles. Okay. Still, this is actually one of the most common methods because it's so easy to implement. If you want to do this thing on your assignment, this would be the easiest one to try. It's still annoying, right? It's still a recursive algorithm with a weird data structure. Okay, so the second most popular one, in case I haven't managed to talk myself into circles quite enough, sort of flips it backward, where we're going to say that my boxes cannot overlap anymore. This is closer to what Rachel is suggesting. So my boxes can't overlap, but what I'm going to pay for that is that I'm going to have to put the same object in more than one box. And this is what that picture looks like. It's called a KD tree. If you've taken a machine learning course or a certain kind of database course, you may have encountered this in other applications. It's kind of a common data structure. Here the K stands for what dimensionality you're in. So K equals 2 or 3 in graphics, typically. Sometimes 4, I guess, if you've got like some weird space-time thing going on. But in any event, this is probably the most popular structure for accelerating your ray tracing code because it's going to turn out to be very efficient to construct and traverse in a very elegant way. So unlike a BVH, a KD tree is a partition of space. No two boxes, with the exception of maybe their boundary line. It's a set of measure 0. We don't really care about it. No two boxes overlap. Right? So the sort of picture you should have in mind is that I take this giant rectangle and I split it in half, and now I take the left-hand and right-hand sides and split those in half, and so on. But notice, for example, well, I've been kind of boring in this example, but maybe this triangle actually touches that second box a little bit. We'll see some examples. So KD tree is a great example of a data structure that's very easy to set up in C++ because we have pointers. In case you guys haven't been frustrated enough with segmentation faults in your code, you're really going to enjoy implementing one of these guys. This is extra credit in your assignment, by the way. This is optional. But essentially, if I want to store a KD tree node, what do I have to do? Well, I have to store its two children. I have to store the dimension along which I split, so x, y, or z. Right, I'm going to put like a little plane. I have to store a number which is the split distance. So when we think about that, it's like controlling the position of this vertical plane here. And then the stuff inside of my KD tree node. That makes sense? So this is a recursive data structure where every box basically stores the two boxes inside of it and any triangles that it has around. Okay. So we have to do a few things. The first thing we have to do is construct the KD tree. The next thing we have to do is traverse it. Right? So first of all, how do we construct it? Well, we start with one giant bounding box around our entire scene. And now I have to make two different decisions, right? I have to decide what dimension. So like in 2D, do I split it vertically or horizontally? Hot dog and hamburger, is it the other way? I never could get that right. But in any event, I have to decide on the dimension to the split and the location of where I want to put it. By the way, usually people, when they choose the dimension, they just choose like the longest one, although the example we mentioned earlier is a good one for why that's not always a great heuristic. Okay. And the annoyance of this entire setup is this green triangle right here. Because what am I going to have to do with this pesky triangle? I'm going to insert him into both boxes. Okay. Right, so what do? I make that decision, I recurse, and now I take each of those boxes and I split those and so on. And until I've maybe reached some minimum number of objects in my box that I'm willing to intersect with, and then I just store them in an array and I'm done. All right, this basic kind of data structure makes some sense? We're going to talk about how to traverse it in a second. Cool. By the way, there are like many surveys, and you write up stuff like different clever ways to construct these objects. There's like lots of heuristics you could cook up, but then you can always cook up some weird counterexamples where they'll lead to like every object being in every single box or something like that. So you really have to think about this stuff pretty carefully. Yeah. It's a great question. Yeah, there are multiple things people do. Sometimes you just cycle. I'd say a more common heuristic would be to choose the longest axis. This is true even in 2D. So let's say that I have a bunch of objects like that, right? So here's my bounding box. I split it vertically. Does it really make sense for me to split it horizontally? Probably not, right? So probably I would split the two children boxes vertically too. So the heuristic here would just be maybe the length of the longest side or something like that. Yeah. Other questions? Cool. All right, so ray tracing with a KD tree is a bit of a different experience because unlike the BVH, if I intersect something in the front box, do I have to check the back box anymore? No, that's the advantage here. Okay, so here's our schematic, which is if I'm a leaf node, well, then it's just a bounding box. I have to intersect with everything inside of it, right? I don't have a choice. I can check the back child intersection, the front child intersection, recurse in both of those. So a very naive kind of version of this might be to just pretend like it's a bounding volume hierarchy. But of course, there's a bit of a redundant computation if you do that, right? Because maybe you can convince yourself that your ray is already hit into something before you've hit that other box, then somehow you really shouldn't have to do that at all. Right? Okay. So let's do sort of a smarter version of that, which is going to be the following. So, by the way, implementing this recursively in a really elegant fashion is actually kind of tricky to do because you have to decide what information comes from the parent and what information you compute in the child. I think every time I've done this, I've ended up having to recompute a bunch of numbers because I can never get it quite right. But in any event, if I did my recursion correctly, then by the time I get to one of these splits, I already know the T start and T end of being in that box because I kind of computed it from the bigger bounding box that contained this guy, right? So the only T that I need to compute is the T middle for my array, right? So I know when it enters the union of these two boxes. I know when it exits, but I don't know the t where it hits the boundary line from one to the other. Does that make sense? So the first thing I do is compute that thing. I already talked about how to do that. That's not so bad. Now, there's like a million special cases that I have to account for. If your instructor managed to do his PowerPoint art correctly, I think I've caught them all in this slide here. They look something like this, which is I could only intersect the front box. I could only intersect the back box, or I could intersect them both. Yeah, makes sense. Actually, I forgot one case, which is maybe I don't intersect the whole damn thing. But at that point, I should not have ended up at that box in my recursive algorithm, right? Okay. So remember that I have these 3 t values, and notice that t start is less than t end. By the way, that might not be the case when I just intersect with the size of my box, because maybe my box is flipped backward relative to the position of the camera, but in that case, I'll just swap the label of which one's start and which one's end. Okay. Right, so first of all, if t is greater than t end, which of these scenarios does it mean that I'm in? The option A, option B, or option C? So again, t, like when I intersect the dotted line, is bigger than t end, which is the time that I leave the box. How many of us vote A? How many of us vote B? How many of us vote C? How many of us can't even right now? Yeah. Okay, the answer is A or D. Right, because think about it this way. I exited the box, and then I kept going, and then I intersected the boundary, the midpoint. So in other words, t was bigger than t end. That makes sense? Similarly, let's say that t is bigger than smaller than t start. How many of us vote option A? Option B? A, B, C? Yep, the C, which I'm standing in the way of. The answer is C, right? Because I intersected the dividing line and then I reached T start. Notice that in both of those cases, do I have to look in the other box? No. It's the only case where I have to look in both boxes is when the t's are kind of ordered, t start, t, and t end. Everybody with me so far? Yeah.
So in this example, we're doing it in two-dimensional space. Would we be doing this in three-dimensional space?
Oh, absolutely. So in 3D, you just have to add a dimension to each one of these arguments here. But I can't draw in 3D. Yep. Okay, so here's our KD tree traversal pseudocode here. This is one of the easiest, most annoying things to get wrong. I encourage you to draw lots of schematics when you're working out your code at home. Right, so what do we do? Well, the first thing is if I'm a leaf node, well then I have no choice, right? I just have to intersect all the triangles in my box and be done with it. That's the easy one. Okay, next I compute that t value. Remember that's that t when I hit that middle guy. And I have to check each of these cases. Right? So remember, if t is less than or equal to t start, what does that mean? That means I intersected that middle point, and then I entered the box. Right? Then I should intersect stuff against the backside of my KD tree. See, backside. Similarly, if t is bigger than tn, I have to do the opposite and just intersect with the front side. And otherwise, to be conservative, I can do one more clever thing to save myself a bit of computation, which is intersect with the front. If I found something there, do I need to look in the back? No. But if I didn't find something, then I do. Does this algorithm make sense? Yes?
What is the
Oh, leaf. Yeah, so a leaf node is just one that holds a bunch of triangles instead of splitting again. Yeah. Any other questions? So this algorithm, notice that it strongly depends on if an object intersects a box, that object is in that box, meaning that the object may be in more than one box, right? Because what would be disastrous would be like a triangle's in both the front and the back box, but for whatever reason, I only put it in the back one and somehow I ignored it. Yeah. Okay. Right, and so that's our computation here. All right, and so, yeah, I don't know why I highlighted all this stuff. So basically the point here is that early termination is powerful. The more computations that you can do, or the more tricks that you can do to eliminate that call to intersecting array with your scene, the better off you are, because those are really expensive computations. Okay, and it turns out that if you construct your hierarchy very, very carefully, one thing you can convince yourself is that often you can make ray casting basically independent of the depth complexity of your scene. In other words, this imbalance between like some pixels taking a long time and other pixels not can really be reduced to almost no imbalance if you set up a really nice kind of isotropic, carefully designed KD tree. On the other hand, it could mean, like let's say that my scene is 99% like pixels that basically contain nothing. It might be I actually increase the cost of rendering my scene because now I have to intersect with a bounding box around nothing and then nothing. Right? Okay. Right, so that's our two main kind of gains here. We only have to intersect with triangles kind of near the line, and if we found in that third case, if we found an intersection in the front box, we don't have to look at the back. Cool. All right. There are many little details here. So for instance, if I intersect an object, so let's say that I'm in this is where things get annoying when you implement these things. These are largely just cautionary tales that I think if I warn you guys about it and you think about it, you'll know how to fix it, but they're things that are worth being aware of. So for instance, here's my KD tree node. Let's say I have a triangle, like that, and I have a ray going through this thing. And let's say I'm checking the front box here. Should the front box say that I intersected a triangle? The answer is actually no. Because you want to say, did I intersect that triangle? And was that intersection inside of that box? Is the only way to make that code correct. Otherwise, you can convince yourself that sometimes you can accidentally eliminate intersections that you shouldn't have. And similarly, you need to take the direction of the ray into account. So like, I've been using the words front and back. But of course, it could be that for another ray, my scene is actually going that way. Like maybe I'm annoying, I have like a mirror behind my object, right? Then what I have to do is swap that label before I call that little piece of code. And of course, you can accidentally divide by 0 if your ray is perfectly parallel to the axis, or I guess in this case, going this way, right? But the probability of that happening is exactly 0. Okay, so yeah, so that's the basic idea of KD tree traversal, which is, again, one of these things that's like conceptually not too difficult, but as you can imagine, coding it is actually quite a challenge. The main challenge in practice is exactly where to put that split and how to construct this tree. In fact, here's a diagram illustrating exactly the effect you're asking about before, where my scene has this like giant void in it, and it's unclear what the best sort of careful place is to put that dividing line to reduce, on average, the number of ray object intersections I have to do. And so there are many different heuristics for that. One very, very simple one is take the longest axis of my box and always divide it in half. I think this is actually the most common one that people do because it's easy to code. But of course, that can lead to pretty non-uniform splits. So for instance, in this scene, there's like just a few triangles over here, but just their presence is enough to drag that box all the way over to the side, which is not so great. Another slightly better one would be maybe to split at the median coordinate. But that that's not really aware of density anymore. That's just trying to have an equal number of things in the two boxes. But there's all kinds of other ones. So for instance, one of the famous ones, which we're not going to cover in this course, but if you're interested in these kinds of advanced topics, is something called the surface area heuristic, where you take your 3D world, you project it onto the one axis of your box, you kind of render it in one dimension, and then you use that kind of signal of where there's stuff and where there's not to choose a reasonable split. Which is a really, at least for me, like kind of difficult thing to wrap my head around how to think about, but turns out to be pretty effective in practice. If you take a computational geometry course, like you go over to take like Piotr's class, Professor Indik, then you'll actually ask slightly different questions, like, can I construct this tree where guaranteed, no matter what direction my array is coming from, I never do more than n log n, intersections, or I guess log n intersections when I traverse, right? Nothing we've done here gets anywhere close to proving a theorem about the number of intersections. That's a tough thing to In fact, I don't think you can when it's bounding, when they're aligned to the axes. I think you need to be able to rotate your planes to do that. Okay, I think we'll split that. So essentially, by the way, one of the kind of interesting observations is often to do these kinds of heuristics, like this cool surface area trick, that's a lot of computation up front, right? You're like rendering your scene to figure out where to place your bounding box. And in practice, oftentimes, you rarely get more than a factor of 2 improvement over like the really naive splits. So this is one of those algorithms where it's not totally clear that it's actually worth implementing. I feel like this kind of thing, there's this gentleman, Ingo Wald, his whole PhD thesis. I wish I got my PhD in the days when these kinds of things could be your thesis, but I'm sure at the time it was really groundbreaking. Covers like millions of different heuristics. It's kind of a fun thing to page through and see all the cool ideas that are there. There are all kinds of different hardcore sort of ways to make this stuff faster, like, doing optimized ray triangle intersections. Like one thing we didn't do when we were talking about barycentric coordinates was like count the number of adds, multiplies and divides, and see if we could like factor that expression slightly differently to reduce that number. A different question is, how do you pack your KD tree in memory? So one thing you might know is that on classic memory architectures on your computer, what's expensive is random access kind of stuff. Like if you think of your memory very abstractly as one giant long line of bits, then what is very pricey is like first getting some bits over here and then ones over there and some over here and so on. So one thing you might try to do is organize your KD tree in memory so that like things that are nearby spatially end up being kind of nearby in your memory. And that turns out can really make your ray tracer a lot more efficient because you tend to grab pieces of your scene where related arrays are, looking at the same piece of memory more than once. Yeah.
Would you have to implement that in like some lower level feature?
Not necessarily. So I mean, in C++, if you just think of storing all this stuff in just a giant array, then your position in that array is more or less your position in memory. These things are heuristic, right? And one thing that you can't do really is control what like crazy stuff your compiler does behind the scenes to, it means well, but maybe it actually does some damage, laying stuff out in a weird way. And then of course there are many different parallel extensions of ray tracing, like maybe tracing 4 rays at a time, or like maybe it actually makes sense to send some secondary rays that were unnecessary, but can be computed using the same path in your CPU, because when they do happen to be useful, then you just have the answer there. These are crazy tricks and ones that like are just if you want to make that ridiculously fast little squeeze of speed out of your ray tracer. Yeah.
How would you, like, is there, I'm unclear about ways that you could combine that with any of the tuning, like, tricks that we talked about, because, for example, like, especially like the recursive one,
Uh-huh.
I
This is a CPU parallel algorithm, meaning that every thread is allowed to do its own thing. Yeah. On the GPU, it is not clear at all how to make any of these tricks work. In fact, the short answer is you can. Yeah. Great question. Any other ones? Cool. All right, so what are the pros and cons? The pros are that the code is relatively simple, deceptively simple, because if you get one sign mistake or inequality backward, the whole thing is verschlicked. It's relatively efficient, but the construction of these KD trees is kind of costly. And there's something that we haven't really talked about is that if you have an animated scene, then KD tree might not be a great way to reduce your rendering time, in the sense that every time an object moves, you have to reconstruct that entire tree, right? So one of the kind of interesting questions might be, so for example, in the bounding volume hierarchy, if I have an object that's moving, what could I do? I could compute a bounding volume for that object in all the positions and all the frames that I'm rendering, and that's a perfectly reasonable conservative thing to do, right? But in the KD tree construction, that's sort of not possible. Okay. By the way, if you want to see a really crazy thing, you can read how people actually do this in graphics hardware. So for the remainder of today's lecture, we'll talk about some of the more exotic options that you might encounter in the wild. I would not recommend you code these ones, but they're worth being aware that like, essentially, graphics is around for a long time, and there's just a million clever hacks people have for accelerating ray tracing in different sort of smart ways. Another one that I think is kind of funny because it's halfway between ray tracing and rasterization, which is what we're going to slowly start transitioning into over the next couple lectures, is something called ray marching. I like that. Somehow it's kinetic, you know. So in ray marching, we do the following. So how many of us have played with like Microsoft Paint? Cool. So you know if you want to draw a straight line in Microsoft Paint, you get that like weird little jagged line that comes out. So there's an algorithm for drawing those lines, which is extremely efficient. And by extremely efficient, what I mean is it runs in time proportional to the length of the line, so you don't waste any CPU time. And how does it do that? Well, if you think of your pixels like little boxes, then what you do is you kind of, it's very similar to that entry-exit computation we did before, right? Like you figure out where you entered that box, then you figure which of the 4 faces do I exit from, and that kind of tells me which pixel to walk to next. So I kind of go up and over and up and over and so on. This algorithm is called Bresenham's algorithm. If you were to take graphics class 20 years ago, you would have spent your first 3 lectures deriving this for a bunch of different shapes like circles and lines and so on. This is no fun and basically useless. It turns out your graphics card, it's actually kind of depressing. It's actually faster to just like check every pixel in a bounding box, whether it hits your line, than it is to use a lot of these clever algorithms. But in any event, in ray marching, I can do a very similar thing in 3D. So what are our options so far? One is a bounding volume hierarchy, where your bounding volumes might overlap. Different one is a KD tree, where I split, but the size of the boxes could be non-uniform. An even simpler thing that corresponds to hashing, if you've ever taken an algorithms course, is to do the following. I'm going to take my whole 3D scene, or on my computer screen, my 2D scene, or in Flatland here, and I'm going to just divide it into boxes. Like I'm just going to choose a constant, which is the width of a box, and I'm going to stick a giant grid on top of my scene. And anytime an object intersects that grid cell, I'm going to stick it in that grid cell. So like this triangle will get put both in this guy and this guy. This is like a 2-dimensional array. Or in 3D, a 3-dimensional array. By the way, what do you think the storage cost is of a data structure like this? Very high. Yeah. So this is maybe something you do at a course level, and then inside of each of these boxes, if you get really complicated, you store a KD tree or something like that. Right? These, you can mix and match these things. Okay, so what am I going to do? Well, I'm going to cast my ray, and now I'm going to call my MS Paint code, and I'm going to rasterize the line that the ray walks along. Right? And what does this give me? This tells me that this is the first box I hit, that's the next box I hit, that's the next box I hit, and so on. And every time I go into a new box, I intersect with everything inside of that box. And the second I find a hit, do I have to do anything else? No, I'm done. So this is an algorithm that is halfway between rasterization and ray tracing, right? I'm tracing a ray by rasterizing the ray itself, which is kind of clever, right? So that's the basic setup in a little bit more detail. Step 0 is create your grid. There's a really annoying parameter here, which is the width of your box, which is hard to choose. You have to be careful because objects have to be inserted into many different cells, potentially. One computation you can decide to do in detail or not, like should I add this triangle to that cell? Probably not, but if I do, will I hurt anything? Probably not, right? So one thing I could do would be just use the bounding box of an object to place it into cells, or I could try and do something more clever. But in any event, then I just keep walking along the ray until I find an intersection and I'm done, right? And so this is like a really clever little algorithm for doing this stuff. This is not particularly parallelizable, so this is not a technique that I think people like too much in practice. As is sort of illustrated here, of course, you can combine this with other data structures. So like maybe every triangle has a bounding box. So after I intersect this object, then I intersect the bounding box, then I intersect the triangle. Or maybe the bounding box has a KD tree inside of it. Whatever, you know. Remember, your ray tracing code is just a thing. Every object in your scene is a thing that takes an array and tells you whether it intersects it. And from the abstraction perspective, it doesn't matter whether it's a ray marching thing or a hierarchy or what. So the advantage here is if you have a fine enough grid, you can essentially just intersect the voxels along the ray. And that's not such a hard thing to do. And so there's all kinds of clever ways that you can do that we basically talked about. One thing to notice is that, of course, the points, like the red points where you intersect the vertical or the horizontal lines here, and the green points where you intersect the vertical lines, notice that these are evenly spaced. they're not isotropically spaced. Like for instance here, the red points are farther apart than the green ones. But by working out this pattern very carefully, you can figure out using actually just integer arithmetic. You don't even need floating point here. Like if I'm in this box, should I move to the right or up? And this is one of these things you can just think through very, very carefully. And so the actual algorithm is really, really simple, right? Like you kind of figure out the next xt and the next yt. You figure out which one comes up first, and then you increment and you either move up or over, and you keep going. It's called a differential analyzer. It comes from like old school video games. All right. Or sorry, not differential. A digital difference analyzer. That's my bad. Yep. And these algorithms are very similar to line rasterization. This is exactly what goes on inside of MS Paint when you draw that little jacket line. By the way, that algorithm falls apart if you want to anti-alias your line, right? Okay. Right, so that's the pseudocode there. If you want to visualize it, here's kind of what it looks like. So I sent out array. This is kind of cute, like pixel universe here, right? So I send array into my bounding box. And then what it does is just traces over these rainbow boxes. Each rainbow box knows what objects in the scene it intersects. And that's what I need to do. Any questions about rate marching? Okay, the advantages here are that this is very easy to construct. It's just a regular grid of boxes. It's not so hard to traverse. You got to figure out that spacing is kind of annoying to think about, but at least in concept, it's not so bad. The disadvantage is that you have a giant grid on your scene, which if you have a complicated scene is probably not terribly practical. Okay, so the next part of our lectures, we're going to start taking notice that we're just going to keep taking our ray tracer and making it more and more complicated, right? So the next part of our course, we're going to ask this question, which is, of course, is ray tracing really simulating physics? And of course the answer is no, right? Your eye is not emitting, like it's not like sending out a little laser ping and then like receiving back the color, right? But rather light just passively enters your eyes. So what we're really doing is what we might call backward ray tracing, right? We're ray tracing from your eye back to the light source. And this really is just a weird trick in an approximation, right? And so for instance, coping with like transparent objects, well, what do we do? Maybe we like multiply by the color of the transparent object. Is that really what the light is doing? No, but like it's some kind of reasonable heuristic. And we notice that we've built up a lot of these things, but we're missing objects like caustics. And so one thing we're going to start thinking about is how to do rendering like this, where here I have, a glass object, and notice that the light is getting redirected every which way as it moves through this refractive thing. In particular, it's focusing on the surface underneath the rotating cube. Will the algorithms that we've talked about so far be able to do that? No, right? Because let's say I'm looking at that surface here, and now I cast a light ray. The light ray is going to go straight up to the light bulb. It's not going to do this crazy path in the interior of this thing to see if it hit the light or not. And so that's where somehow we still got a bit of a question, right? Which is how to simulate these sort of effects. So what we're going to start talking about, although of course we're low on time today, is forward ray tracing, where we're going to shoot out lots and lots of photons from the light source. But now, of course, there's an extremely low probability that they actually reach your eye, right? So here's a visualization of what this looks like. So here I've got this lamp, and I'm going to just start randomly scattering out photons from the lamp. So I'm actually going to simulate the physics. And then eventually going to bang into the wall. And I'm just going to keep it. Just keep it there in sort of a forward pass before I do any of my rendering. The question is, how can I make that useful? So this is what I want you guys to ponder for our next couple lectures. We've talked about backward ray tracing from your eye to the world. How can I make forward ray tracing efficient, right? Because 99.99999% of those photons I sent out is never going to hit my eyeball. That's what's going to lead us to some techniques called global illumination, in case you want that nice warm glow of your room that you're going to render. By the way, these data structures we've talked about today are absolutely critical in that world, because how many photons am I going to need? A ton. And so I'm going to definitely want to store these things in a KD tree. Okay, so anyway, with that, that's today. As a reminder, again, on Tuesday, your lecture will not be filmed. Our lecturer will be David. I'll be here. You're welcome to give me a hard time, and I can't say anything back. It'll be a weird day for all of us, and I'll see you then. So have a great weekend.